Everybody excited for learning about the Earth and the atmosphere of the Earth and how it compares to other planets and things like that? Yeah. Cool. So that's what we're doing today. So I'm glad everybody's equally excited about this. So Earth's atmosphere. So there's a few things we need to talk about when we talk about our atmosphere. The first thing is probably how it got here in the first place. So Earth's atmosphere formed from gases in the protoplanetary disk. So pretty much everything in the universe is made of hydrogen and helium. Those are the predominant materials or elements in our universe. And that was no exception when our solar system first formed. It was pretty much all hydrogen and helium left over from the Big Bang, actually, is where that originally came from. And as the Earth formed, that first atmosphere that we had, the primary atmosphere for Earth 4.5 billion years ago when it formed, was also made of pretty much all hydrogen and helium. So here's a question. Do hydrogen and helium have large or small masses compared to the other elements? Up, yes, large, down, no. I see lots of thumbs down, and that is correct. Hydrogen is the first element on the periodic table. It sticks around in a pair, so it's usually H2 is how you say it because they're bonded together. So the atomic mass of that is 2 because there's 2 protons, so 1, 2. Helium has a mass of 4 because it has 2 protons, 2 neutrons in that nucleus. So as a result, what ended up happening for the very early Earth, we had this very early atmosphere, is it was very easy for this material to basically escape into space. They're very light materials, and the Earth did not have enough gravity to basically hold that all in place. And because also, the other thing is light atoms move faster than heavier atoms. So it was also very easy for these things to escape because they're ricocheting all over the place, and it's much easier than to escape over if you're just going very slowly back and forth. So that didn't last very long, maybe a couple million years or something like that. But then lucky us, we have a secondary atmosphere. So this is after that primary atmosphere, this next atmosphere that the Earth had. It was actually formed from a couple different things. The first is early Earth was a very active volcanic place. Of course, we've discussed this week about plate tectonics and how we have volcanism on Earth, but there was even more of it when it was still very hot and hasn't cooled as much as it had today. So you had a lot of outgassing from all these volcanoes that were occurring on the early Earth that created a lot of the materials in our secondary atmosphere. But in addition, we had a lot of impacts in the early days of the solar system. There's a lot of debris left over, a lot of comets that had a lot of water ice, things like that. Lots of impacts were happening in those first 100 million years tops. And the reason that's important is that's probably where we actually got most of the water on our planet was from these impacts. For reasons I'm not going to get into in this lecture, it's very tough to have water survive on the surface of the Earth in those early, very volcanic molten days. So it probably had to have formed, and then we got water later, thanks to things like cometary impacts of our planet. So the second atmosphere was actually very dominated by water. It was almost 60% water. Carbon dioxide also made up a decent fraction, about a quarter of what we had in that atmosphere. Sulfur dioxide, a respectable amount. And then we had a little bit of nitrogen and some noble gases. What then happened is, years and years and years and eons passed. So we ended up having a very different atmosphere now, lucky for us humans who breathe something that is not very present right now in this, compared to what we have today. So our current atmosphere is actually 78% nitrogen. The nitrogen doesn't really do anything for us. It's just there. The part that we are very happy that we have is oxygen. About 21% of our atmosphere is oxygen. The noble gases are still about 100%. Very tiny amount of carbon dioxide. For the amount that you've probably heard about carbon dioxide in our atmosphere, it only makes up 0.04% today. Then, of course, we have a little bit of water in the form of water vapor in our atmosphere. I mean, clouds, right? Stuff like that. And a tiny amount of sulfur dioxide. So now that we've gone through these two, I'm going to put the two side by side. And we're going to discuss the really big changes in Earth's atmosphere from that secondary atmosphere that was created to what we have today. So probably the most important one is water. We used to have a ton more water in our atmosphere than what we have today. So I'm going to ask you guys why you think this is. What do you think happened to the water in Earth's primary atmosphere? And I'm going to give you some options: condensed into liquid, froze to ice at the poles, evaporated into the air, or floated off into space. Okay, I have a pretty big diversity, so I think we're going to walk through this because I think this question is actually, you need to think about it for a minute. The answer is it condensed into liquid. We have oceans on this planet covering 70% of our planet's surface. So basically, when this was originally in our atmosphere, it eventually then condensed into liquid, and that is what forms the oceans and all the liquid water that we very much appreciate on this planet today. Of course, I saw a lot of bees out there. You're not wrong, but it's a very small fraction compared to the amount of water in our oceans. About 2% of all the water in our planet is frozen in ice currently at the poles of our planet. So it's really not, it's a fraction, but it's not a huge fraction compared to just the sheer volume of our oceans on this planet. Okay, so what happened to the secondary atmosphere is the water condensed. The next one we can consider is the CO2, or the carbon dioxide. So what happened to all the CO2? So you have your very early Earth. You have all this carbon dioxide in that atmosphere. The CO2 is then actually absorbed over time by water once the water was no longer in the atmosphere. This produces acids and bases and chemically react with rocks, which locks the carbon into solid form. So limestone, for example, is created when carbon dioxide has a reaction and then forms into a rock form instead of its gaseous form. So the CO2 goes into the ocean and it ends up staying in rocks at the base of the ocean. The other example in the ocean, by the way, is seashells actually have a lot of carbon dioxide sequestered into it. So then those seashells will stay in the ocean until plate tectonics basically brings those back into the core. They can come up again through volcanism. The other thing is plants absorb carbon dioxide and they will sequester it underground when they die. So, if you have a tree, any tree out here in Eugene or beyond, trees are breathing in carbon dioxide and exerting oxygen through the photosynthesis, how photosynthesis goes. So, anything that you had at the time, for example, 200 million years ago, if you had a tree, that tree eventually dies, it ends up going in the ground. And then that's actually what oil is materials from the age of the dinosaurs that was organic, had carbon dioxide in it, ends up in the ground, turns into oil. So the fact that you're burning oil, this carbon dioxide comes out. We're going to discuss later today why that's an important effect. So carbon dioxide has been absorbed. Where did the sulfur dioxide go? That was the third one here. And you can see that we basically have no sulfur dioxide today. It's a very, very similar process to carbon dioxide, where it's absorbed by water and sequestered into the rock as it interacted with water. So if you heat these rocks or anything like that, as I said, that carbon dioxide or the sulfur oxide will go back into the atmosphere. Okay, so then next thing, nitrogen. The nitrogen survived, yay. And that is why nitrogen is 78% today. It stayed the same, it's just our atmosphere is much thinner than the initial secondary atmosphere that we had. The next thing to say is, where did the oxygen come from? So we have no oxygen in that secondary atmosphere, and we have 21% in our current atmosphere. So basically plants. Photosynthesis, as I said, takes in carbon dioxide and releases oxygen. So it's basically because of plant life that we can breathe on this planet. Most of the oxygen in our atmosphere is not actually from plants like trees or flowers or anything like that, but actually plankton and algae in the ocean is primarily where we get our oxygen from in the atmosphere. This is actually an important one because it turns out oxygen as an element, it very rapidly oxidizes. So if you don't keep replenishing oxygen in an atmosphere, it disappears within a few thousand years. It's like a very, very quick process called rapid oxidation. This is why sometimes you'll hear about astronomers when we're looking for signatures of life on planets around other stars, we're looking for oxygen signatures. And that's because you need to have something constantly putting oxygen out into that atmosphere. And on Earth, that is basically because of plant life. So that's why we're very interested in finding oxygen on other planets. It's not that there might not be other things that aliens could breathe, but on Earth, it's a very good indicator that we have a significant oxygen in our atmosphere due to the life on our planet. So the oxygen is due to photosynthesis. So that's where everything came from. And now we're going to talk about the Earth's energy budget and how this affects our atmosphere and in our environment on Earth. So when we think of the Earth, pretty much everything on this planet is powered by solar energy. I mean, we have some geothermal stuff going on thanks to the volcanoes, but obviously life and everything that we have on our planet only exists because we have the sun and all the solar energy coming from the sun. So as we have the sunlight coming and hitting Earth, you will then have infrared light that is radiated from the Earth. So if we had no atmosphere, to be totally clear, our planet would be very cold, not very nice place to live. Basically, the fact that we have our atmosphere is why it is warm enough for us to survive and have liquid water on our planet. So what happens is, as I said, the sunlight comes in, and then you have infrared light that is radiated out from that sunlight. So here's a question for you guys. If the Earth absorbs more light from the sun, it gets hotter. So what is then going to happen to the infrared light that the Earth emits? Okay, I'd say the threes have it. Yes, so more energy then is going to be emitted as infrared light. The way to think of this, if you have a coffee pot and you're putting it next to a heat source, it's going to then become hotter, which corresponds with infrared radiation. Another way to think of this on our own planet. So sure, a lot of you guys have gone out, at sunset or right after sunset on a beach. And if you walk barefoot on the sand, you notice something about the sand if it's been a very hot day. Does anybody know what that is? What I'm thinking about? Sand will be warm under your feet, right? If you're walking after it's been baking in the sun. So that's basically what happens. The sunlight is hitting the Earth is radiating, giving off heat because it has been hit by the sunlight. So when we think of the energy budget of our planet, you have to think of things like the flux and the temperature. So the energy that comes into Earth is going to equal the energy that goes out into space. So if we think of the sunlight hitting the Earth, it is going to have to equal the infrared light that is radiated by Earth. The important thing to note is that the sunlight hitting Earth depends on the energy flux, and the infrared light that's radiated depends on temperature. So these are two different things, the amount of light coming in and how hot something is, but they will reach equilibrium. So if the sunlight hitting Earth goes up, then the infrared light will also increase, as we said in that question. So the equilibrium temperature, as a result, is the temperature at which we can say that energy in and energy out are balanced in a system, is what the equilibrium temperature is going to be. The trick about all of this, though, so the Earth is not a perfect mirror, and nor is the atmosphere a perfect mirror either. So we're going to have something called reflection. So as the sunlight is going in and hitting Earth, you're going to have the infrared light that is going out, as we just covered. But you're also going to have reflected sunlight. So not all the sunlight comes in perfectly to our planet. Some of it is reflected in our atmosphere. Not all of it, but some of it definitely will be. And you're also going to have some of the infrared radiation that's in the atmosphere is going to be absorbed and then re-radiated out from Earth. It's not a perfect system that it immediately escapes the atmosphere, captures things, and it takes a little while for that to escape. What this ends up meaning is we have what can be called a greenhouse effect. So greenhouse gases, carbon monoxide, carbon dioxide, methane, carbon dioxide and methane are the ones that you tend to hear about the most. So they don't absorb visible light. So they don't absorb the sunlight. That just comes to the ground. What they do absorb is infrared light, so from the sun and from the Earth. And after they absorb, they're the ones doing this re-radiating in our atmosphere of infrared light to Earth and to space. To be completely clear, we need some of this to exist because, as I said, if we did not have this atmosphere, it would be too cold on Earth to survive. So we have our energy budget. So energy into Earth, energy out into space. One depends on flux, one depends on temperature. So we also have this thing, reflected sunlight. So on one side, the energy into Earth, not all of that sunlight is going to come in. Some of it is going to be reflected. That depends on how shiny, basically, is what albedo is. Albedo is a word for just how shiny something is, how reflective a material is. And then on the right side here, so the energy out into space, we have the infrared light radiated by Earth. And then you have to subtract the infrared light re-radiated from our planet. So what happens then? If we have the Earth in balance, you think of a teeter-totter. On the one side, you're going to have the energy in. The other side, the energy out. Everything's in balance. We have a nice system in place and a stable atmosphere. What we're going to have on the one side, the energy inside, as I said, the reflected sunlight, the sunlight hitting the Earth, is going to be balanced by that infrared radiation re-radiated and the infrared light radiated by our planet. If we have an unbalanced energy budget, on the other hand, the temperature of our planet has to change until this teeter-totter is back in the balance. So if you have more energy going in than out of a system, you have to have higher temperatures because that's what determines how much infrared light is radiated outward. And you're going to have more infrared light radiated. If you have also more energy escaping than entering, you're going to have, on the other hand, lower temperatures. This has happened, in Earth's history, and you're going to have less infrared light radiated. So, as I said, this has happened naturally many times over the course of Earth's history. Things get out of balance for whatever reason. Either the sun has been different or there's different atmospheric effects in our planet. The Earth adjusts, and then it rebalances at a new equilibrium. So if we think about our teeter-totter, this is the visual representation of this, the sunlight hitting Earth, the energy in, more energy in than out, you're going to get higher temperatures. So here we have an out of balance teeter-totter, and the infrared radiation re-radiated from our greenhouse gases is going to come back to Earth, and this is going to give us higher temperatures on our planet. If, on the other side, you had more reflected sunlight, then you would have more energy escaping than entering, and the temperature on our planet would lower. So then, of course, it's in the news a lot, Earth's changing climate. How does this relate to what we just talked to, Earth's changing climate now versus the rest of our history? So climate is the long-term average of weather. So climate is what you expect, weather is what you get. So if you're talking about what is the weather going to be like in Eugene, Oregon, 5 days from now, you have some sort of idea to maybe 60% accuracy. What's the weather going to be like in 100 years from now? That's climate. We can't predict what exactly, is it going to be sunny or rainy or whatever. So one marker of how to predict climate is global average temperature. And there has been, over the last century or so, a trend which corresponds with an increase in temperature on our planet that is about 1 degree Fahrenheit, in Celsius. So I'm sure you guys have heard about this before. One thing you might not know is that for millennia, atmospheric carbon dioxide, which we think is what is driving this increase in temperature, the reason we're very concerned about this increase is as industrialization happened, we started burning up the coal and oil, which we talked about has carbon dioxide in it, burning it up in our atmosphere. The current level of carbon dioxide is much higher than basically anything we've seen on this planet since humanity has existed on this planet. And we have this increasing temperature trend. So we have a system that is very not in equilibrium right now on Earth. This is data from Mauna Loa, which is a mountain in Hawaii, very pure atmospheric temperatures. The variation, by the way, that you see from year to year, that's because there's more landmass, more trees in the northern hemisphere than the southern hemisphere. So you will have a variation just due to the fact that there's more things absorbing carbon dioxide in the summertime than in the wintertime on this planet. So climate change is due to increased carbon dioxide. And what happens is basically we are out of tilt right now. Basically, as we put more greenhouse gases into our planet's atmosphere, we currently have to then raise the temperature of our planet in order to put the system back into equilibrium. So as we put in more carbon dioxide, you have to balance with a higher temperature. So to be totally clear, like, this is unprecedented if you look at the history of our planet, the amount of carbon dioxide that is going into our atmosphere right now. It's not that there hasn't been hot periods in the past. It has never gone in so quickly. And also, our human civilization is built on having a certain temperature on this planet. We have the majority of our population lives near coastlines, for example. If the temperature gets hotter, the polar caps melt. We get a lot more flooding in a lot of low-lying areas. That is a billions and billions of dollars problem, or trillions even, for our planet. So when we talk about climate change, it's not that, as I said, things have changed, but what right now is happening is we are the ones putting this carbon dioxide in the atmosphere to limits that we really honestly don't know the full consequences of what's happening. And that's why it's a very concerning problem for our climate and for ourselves.